So thank you. So as we know, I'm Adam. I'm the hardware manager at SKARAB, which means I run the hardware firmware group. Wesley, Mish, and Omar are part of my group, and we're going to have some new members soon. So my role is specifically to optimize the tool flow for the SKARAB and look at new generation hardware, and specifically optimize the tool flow for the correlated beamformer team. So what I've decided to do is tailor my presentation very much in the spirit of PIA, an educational way. So in terms of, we've designed the SKARAB, we have a tool flow, but I want to show kind of with the pitfalls we fell into so that you can see when you look at your own hardware design, how to go about it. So first of all, I'll give a brief SKARAB overview because a lot of people have spoken about it. And then Carrie gave a very good talk on FPGAs. There's just a few things I'd like to just kind of round off on that, and also that will complement my presentation. And then lessons learned 1 to 10. Actually, there were 11 or 12 lessons learned, but I've summarized into 10 lessons. And then the conclusions drawn from that. And if there's time, questions. So I'm going to have to speak very quickly because there's a lot to cover. So pretty much this is the SKARAB. You've seen this picture. We do have LEDs, and yes, they do toggle, and they do give you functionality. We didn't have LEDs. We were on site. The board didn't boot up. We didn't know what was going on, so we put in LEDs. So there we go. So all the functionality can tell you what's going on. Those are hybrid memory cubes, which you haven't probably seen before with the heat sinks. They are high-speed 40 gigabits per second serial memories. Our processing is roughly about 28 gigabits per second, so we need the 40 gigabits per second. And our Ethernet is also 40 gigabits per second. So here is breaking it down in more detail. We have a Vertex 7 chip. What does that mean? It's pretty much that we have pretty much 680,000 logic elements and resources. We have 3,600 DSPs, digital signal processing blocks, and VRAM, 52 megabits, of which the correlated beamformer crowd use like about 98% of that on certain designs. So we really push. We have a quad SFP plus, which means 40 gig, four of them. We have lots of heavy in transceivers. So this is a very different board, and they're very heavy in transceivers, very little GPIO, general purpose IO, but we've kind of got it all working now. 3 hybrid memory cubes, same configuration, whether it's an F engine or an X engine. We also have a 1 gig interface, which we don't use on site, but we use heavily in debug. We have a USB interface, and typically we use that just for serial COM debugging. And a COM Express, which we don't use, but if you have an external processor, you could have an external processor there, but we use the microblaze technology. So you've all seen this. I'm not going to go too much into the diagram. iBob, Internet Breakout Board, Roach and Roach 2s. It's old technology. The new tool flow doesn't support it. I'm in this domain, SKARAB, Snap, and Snap 2. Snap 2 by far, I think, stronger than SKARAB in terms of, as you can see, the logic cells here. Almost 1 million gates compared to our 693 gates. You can't say that a SKARAB is better than the Snap. Snap has got 12 ADC inputs. SKARAB's got 4 ADC inputs. We don't really use the ADC. We do sampling at the feed. So you can't really compare, but we do have HMC on there. And HMC is obsolete, by the way, and I'll get into that. So let's get into some terminology. So Carrie did a very good presentation, and she showed that the transitional time of was at the clock. But in reality, all integrated circuits have a setup and hold time. So what I mean by that, if you look at any data sheet, you'll see this TSU and TH, setup time, the minimum time for which data must be stable before clock transition. It's this time, okay? If this data were to transition, what that means is to go from one value to another, in this point, it's going to violate that setup time. It hasn't had enough time to stabilize. And then you get metastability. What is metastability? Well, it's not 1, it's not 0, it's something in between. And what does that mean? It means, well, I'll give you an example. In radar signal processing, if you will get a target, a false plot, or a false track, in radio astronomy, you'll get a false spectrum coming through. You don't want that. Metastability is your enemy. So always be in mind of setup and hold times. And it's everywhere. So if you violate this window, you're in trouble. So keep that in mind. Next thing, why is time enclosure on an FPGA important? FPGA has no knowledge of its external logic it interfaces to. If that's a memory, if that's an ADC, inputs and outputs, it has no knowledge of it. How can it? the setup times and hold times are specified in the data sheets of the devices. There's also PCB trace length that you need to take into account, the delays, clock skews, all of that. So what does that mean? That means you've got to create a constraints file for your FPGA, clocking, inputs, outputs, and exception constraints. So all your inputs have to be constrained, all your outputs have to be constrained. An exception means, for instance, FPGA assumes that every clock cycle, the data must be, for every clock cycle, I expect that data to be valid. But sometimes a divider takes more than one clock cycle. It takes 4 or 5 clock cycles. So you specify constraints. And sometimes you're not interested in the bars, so you set it to false path. This is the number one reason people don't get into FPGAs. And from what I've seen in my experience, very few people understand timing closure. And often they'll say to me, I'll look at it and it's not constrained. And they'll say, yeah, but it's a low frequency signal. And I'll say, you must constrain it, because if you don't constrain it, you might be hiding other things. So it's critical in FPGAs. It avoids metastability. So what's the next one? Clock domain crossing. Harry mentioned it. If you have multiple clocks, you need clock domain crossing. It's important. Why is that important? Metastability again. So imagine this is an asynchronous system here. Imagine you've got data coming in, clock 1 goes through here, being sampled by clock 2, data coming in. If you look at it as a scope, you're going to see the data and the clock just shifting from each other constantly when you look at it as a scope. And then obviously you're going to have setup and hold time violations. So how do I prevent that? I put in synchronizers, or I can put in a FIFO. If I've got data coming in every clock cycle, I'll write that data into a FIFO, which synchronizer, and that's using the BRAM on the FPGA. Or I can use synchronizers, which is kind of using this D-type flip-flop. So instead of having, so if I want to synchronize this data on clock domain 1, all I do is put C2 over there. There's a chance of metastability over here, but by the time we move to this flip-flop, there's less of a chance of metastability. And if I put another flip-flop there, triple register it, there's even less of a chance. Not to say you won't get metastability, but there's less of a chance of metastability. I'm not going into too much detail there because I've got a lot to cover, but in a lot of documentations, they'll tell you that. And then sometimes you just like the microblaze is sending some messages, and so you're just sending for instance, IP address, but it's on a different clock domain. The thing is, it's still data. You don't just want to send it and hope that you don't get a metastable state. So you have what I have named static bus data valid synchronizers. So what you do is you have a data valid with the data, and you synchronize it using this scheme, shift the data valid, and then just use the data valid to read in the data. By that stage, it's stable again. So those are the techniques. So what were the lessons learned? So we sent out the SKARAB we wrote the spec. We sent it out for tender. Perelix, which is a company in South Africa, high-speed design, very good, designed the SKARAB for us. Gave us a SKARAB, gave me a CD with the firmware on. And when I looked at the firmware, single clock domain, not a single MMCM, which is a mixed mode clock module, known for digital phase-lock loop. What that meant is everyone knows if you use the tool flow or digital signal processing, it runs at like 240 megahertz. This was running at 156.25 megahertz because that's what the 40 gig was running at. What it meant is I now had to go put in all this clock domain clocking architecture, which meant putting in more FIFOs, synchronizers, using more resources. The reset architecture was also affected by that as well. So conclusion is what we should have done is probably specified it better in the specifications, actually specified the firmwares, and actually create a proper block diagram of the desired clock, because we had to do that. So always do that from the beginning, whether you're outsourcing or not. Next step, resets. So when we got the firmware as well, I think there was multiple Perelix engineers working on it. We had a mixture of synchronous and asynchronous resets. If you speak to the experts, some say you must use synchronous, and others say you must asynchronous. If you do a Doulos Vivado training course, they say don't use resets. So you're going to have timing things. So the thing is, yes, but radar astronomy can be complex. You've got state machines. It's always a good idea to have a reset. I typically go for the asynchronous reset. Never had any issues. I'm happy with that. So if you implement a reset, make sure it's properly implemented. So Robin van Dijk, my colleague, who did a really great job on the microblaze, we had a particular issue where the reset to the microblaze wasn't asynchronous reset, it wasn't a synchronous reset. I don't know what it was, but So what we did is, so happened is the microblaze booted up in a different, in incorrect sequence, which caused the board to hang. So we fixed that by putting in a proper asynchronous reset. So if you're going to do a proper asynchronous reset, you assert the reset asynchronously, which means it doesn't look at the clock. But when you desert it, you must do it synchronously on the clock edge. Otherwise, you've got metastability again. If you have different clock domains, you must have different resets. We've done that, never had a problem when we've done it that way. So here's an example in VHDL. That is a synchronous reset. I'm using the MMCM locked, and I'm using the external FPGA pin. And you can see when there's a reset, it gets reset, and then it uses the clock to deassert synchronously. You need to point out that if this is not written properly, you may simulate it, it may work, but there's something called inference. When you synthesize, the synthesis tool might not map that through to a synchronous flip-flop, or a synchronous register there. Like a state machine, it may not infer properly, and so your hardware may not work. So you've got to keep that in mind as well. So always keep to one reset and implement correctly so that it infers a synchronous reset. Avoid the metastability issues. Then we also had a 1 second specification saying we must configure the FPGA in 1 second. What that meant is can't do it through the flash. It takes longer than 1 second. So Parallax had to think about it, said, well, we have to use an SD-RAM, but FPGA and SD-RAM are not compatible to boot from. So we'll put a Spartan device to create a pseudo NOR flash interface. So what we do is we power up. We've got two images in there. We've got what Xilinx's golden image as a safe image and the multi-boot image which we boot from. And then we upload our images. So we don't use FPGAs in the typical way that everyone else uses FPGAs. We have a different image for a 64K, 64 antenna, or sorry, 64K, 32K, 4K, different types of images. And we have to do observations every 20 minutes. So what type of issue did we face here? This wasn't triple registered or double registered, which meant this thing thought that it was booting up from the SD-RAM and not the flash, and there was nothing in the SD-RAM, so the board just hung. So you had these kind of issues. So we're investigating, because FPGAs have got their own volatile memory on now, and we're investigating, and Benjamin Shtopi and Amish Patel will talk a bit about that partial reconfiguration, where you can get access to this configuration memory, so that you don't have to worry about these devices. So keep your configuration simple, no need for complex schemes. Moving on, looking at lesson number 4, tight or incomplete specifications. Yep, we've mentioned that one. That wasn't good. This culprit number 2, shall provide for boot image that must be programmable via JTAG and 1 gigabit interface at runtime. Oh, that's great. Problem is we've got a 40 gig interface. So when the firmware was delivered, I couldn't configure via the 40 gig. So I had to spend all the time putting that functionality in. Also, there were no real firmware specifications for the board support package, which is all the drivers around. So we spent a lot of time now from 2016, 2019, fixing a lot of that stuff up. So make sure your specs are always relevant and achievable. Specify all interfaces and BSP firmware functionalities called interface control document. Always do it. And make sure, in this case, the clocking and reset architecture was missing. And then there were the memory. So I think a lot of people have already covered this. Xilinx has covered this quite well between HBM and HMC. We're headed to HBM. So the red is the important part. Okay, obsolete. Micron decided there's 4 gig memories we have for HMC. We're not going to make them anymore. We go back to the 2 gigs. They had issues with temperatures and so on. So now we're stuck with obsolete memories. HMC is slightly different. It's split into a whole bunch of memory controllers. It uses SD-RAM, so it's got capacitance. So it has got refresh cycles, which means that when you address something, it may not be ready, so it sends you a different address. So it's got a tag. So what happens is the data comes back out of order, so you've got to reorder it using on-chip memory anyway. That's a bit of a pain. It uses a protocol, floating unit, the first 2 letters and the last 2 letters. Protocol is also painful as well. It's not as intuitive. And of course, all these memories have initialization, calibration. They have to do QDR, quad data rate, double data rate. They all have those. And we had this. This was a big one. Took us months. We put a plaster on it and sorted the issue out. So we're moving away from HMC. The HMC consortium, HMCC consortium is obsolete as well. And HBM is the future. There's no silver bullet when it comes to memories, but always test your initialization over multiple reconfigurations. Moving on to regression testing. So we have modules 1 gig, 40 gig, and HMC. So you've got to make a change to a module that already exists. You test the change. Does it not work? No, redo it. Then you have to you have to get to the high level. In this case, it is the correlated beamformer team. If you just test and think, okay, it works, move it to there, it's no longer working. So we started implementing a whole set of regression testing. And we do that by using like SLX models and Python scripts that test it on the hardware. And what regression testing does is it tests the new functionality you have, as well as all the old functionality as well. So it makes sure you don't break anything. So it's very important to have regression testing when you do something like this. Otherwise, high-level guys will always come and say to you, listen, you have to redo this. The next step is number 7, aim for final architecture from the start. I wasn't very familiar with the tool flow we started, so what we kind of did is wrap the Parallax, BSP, and Microblaze in the 40 gig yellow block. And then we noticed that Max Planck, for instance, wanted to use multiple 40 gig cores. So now we had to kind of extract that, even though we're not using multiple 40 gig cores. So we spent the last couple of 2 years trying to do that, and we're getting close now. So now we have a version that has SKARAB, BSP, and Microblaze, and multiple cores. So always do it properly from the beginning. You never have time to do it right afterwards. So if we were to do lesson number 8, do it again. Parallax did the hardware, they did the firmware, they gave it to us, and then we spent the time figuring it out and Kasparizing it. If I were to do it again, I'd do the hardware, I'd get Parallax to do the drivers, and then we would take it, start at the same time with the firmware. We have a better understanding of everything, and then I think we could do it less than 2019. And there were also other issues. Parallax delivered the test hardware and test firmware before SKARAB was Kasparized. So we had Windows test platforms. We don't use Windows, we use Ubuntu. So get involved from the beginning, prevent code rewriting, otherwise specify full firmware requirements. Number 9, and we're getting there, we had stick to a single bus architecture. We use a Microblaze, which is AXI. Our yellow blocks and everything used a wishbone bus, so we had 2 buses on top of each other. Not only that, the clock was driven by 156.25 for control messages. It's unnecessary. You can use a lower clock frequency. We had timing issues when we mixed with the digital signal processing. So we dropped it to 40 megs, and that saved us some time. So bottom line is use AXI only. All chip manufacturers seem to be supporting this. Don't be afraid to drive your bus at a lower clock frequency for control, even if it means multiple clocks. I've shown you how to kind of go about sorting that out. And lesson number 10, if you're in radio astronomy, non-military environments, don't be afraid to start again. So this is what we presented in China last year. We presented, we're going to use now for our SKARAB 2, Xilinx Ultrascale Plus HBM 37P. But not only that, we're going to have 4 of these boards, 4 FPGAs, FMC Plus, 200 gigs. Looked good. We then started to look at the thermals. Omar has got a very good poster on this, on the cooling. And then we started looking, okay, let's ask the price. $55,000. So I'm pretty sure if I asked Patrick nicely, he'd probably give it to me for $1,000. But we have 4 of those, 55,000 times 4 times to convert to rands. It's not going to happen. So existing commercial off-the-shelf boards with 37 UP that go for $9K. Now that, I've got this board, but these commercial off-the-shelf boards, and everything is going towards PCI Express as well. And it means you can mix FPGA, GPUs, and MCUs all in one server. So here's a list of all the Casper hardware that we're utilizing. I'll go through quickly because I am running out of time. So we're using the VCU1525, which is now obsolete, and the VCU118 to do 100 gigabit development. And Benjamin Schlope will talk about that development. You can briefly see it's a PCI Express form factor. It's a 9P, smaller FPGA, 100 gig. Component memory, it's got some DDR4, which we don't really worry about, but you can see the cost there, $7,000, not bad. Is it Kasparized? Yes, so just bear that in mind. VCU128, it's not quite Kasparized, but we're looking at Kasparizing it, so that's in the process. And it's got HBM, PCI Express, and let's move to the last one. Alveo U280, we've just bought 2 of those. This is what we're focusing on. Patrick spoke a lot about that as well. And that's about 6.5K. And I've just found out it's got an XCV37UP on, which is great. The ZTU 111's already been spoken. RF SOC, that's about $9,000. And Jack mentioned the ADM PCI Express Alpha Data, about $10,000, not yet Kasparized. And of course, our Repetiers which have been Kasperized, but it's an educational platform. So it's just used to get into the tool flow and to understand. And we'll be talking more about the tool flow in the breakout sessions as well. That's it. Thank you.
So officially we don't have time for any questions.
I think I got
one question. Okay.
Okay, so this is hardly a question, but just as a service to the community,
Yeah.
I think we should list the Roach 2 as deprecated.
Yeah, the Roach 2 is being deprecated.
You have down as active.
Yeah. So Roach 2 is deprecated, and we don't support it in this new tool flow at all.
The issue is that you use the Roach 2 and they're kind of old, they're actually not going to fabricate them anymore, but you're constrained to using the old tools, and that's the killer. That's the killer for us as well.
Yeah, it's killer. It is. So, just to say, the old tools are completely in MATLAB. There's no Python or anything like that. Sorry?
I have one real question, which is, you talk about timing closure and you link it to metastability.
Yeah.
In my mind, lack of timing closure perhaps gets metastability, but maybe just if your logic just doesn't work.
Yes, so that's the other thing. Yes.
Always
Yes.
metastability. Metastability is the corner case of lack of timing.
Yes. But sometimes, so if you get a whole time violation, for instance, the symptoms might be that your logic just doesn't work at all. But if you get a setup a violation, then it might be that you'll get these spikes coming through your data and so on. Yeah. Sorry. Am I taking your time again?
Thank you very much, Adam.
Yeah, sure. Good luck.